There are all sorts of different types of sequences like we saw before, like there's a Fibonacci sequence, the harmonic sequence, the arithmetic sequence. This one here is called a geometric sequence. So what is happening as I go through this progression? What's the pattern? I go from 3 to 6, 6 to 12, 12 to 24. Well, the pattern that I'm observing here is a times 2 pattern. So this is different than our arithmetic sequence where we added. Here we're multiplying. So we are multiplying by 2 or doubling. Or in other words, doubling. So we can predict the next term. The next term is going to be 48, then 96, etc. And this grows much quicker than arithmetic sequence. So here we have a geometric sequence. Each successive term is going to be formed by multiplication. And we call that multiplier a common ratio. So we multiply by a common ratio. So in this case above, it was times by 2, so their common ratio is 2. In this case here, we're halving. And so our common multiplier is, we can say our multiplier is 1/2. So we times by 1/2, times by 1/2, times by 1/2. So our common ratio we call R. In this case, the common ratio R is equal to 1/2. And we end up with a general formula for this geometric sequence. And basically it works like this. We start at some term A, and then we multiply by the common ratio. Now to get because n starts at 1, we have to make sure that we don't multiply the first term by the common ratio, so we need an exponent of n minus 1. So again, notice this n minus 1 is similar to the arithmetic sequence. The n minus 1 actually represents the number of steps from 1 to the last number n. Okay, so n minus 1 represents the steps from the first number to the last number n. And so this is our general formula. This calculates the number of times we multiplied to get to n. So for example, if t10, the 10th term, we start at A and we multiply by R 9 times because there's 9 steps from term 1 to term n. So basically what two terms allow us to write a general formula for a sequence. And for any sequence, we need some starting point, which we call A. I think I did it in green up here. Okay, the A term is our T1 for A. Okay. And we need to know how it progresses. So how it progresses is for an arithmetic sequence. For arithmetic, we can use our common difference D. What we're adding on each time. For geometric, we're going to use the multiplier R. So times R versus plus D. But basically both of these things tell us how the sequence progresses. So we have a starting point and how it progresses, and that will describe the general formula for a sequence, because that will allow us to work out every term of that sequence. So if we take a look at this sequence, we're going to need, first of all, to make sure whether, now that we have two different types of sequences to work with, we need to differentiate between a geometric versus arithmetic. So we have a geometric sequence in this case. And we're going from, we know that T3 is 40, T6 is negative 625. So I'm just going to list out the sequence, since 6 terms is actually small enough that we can probably just see what this looks like. And we want to know the general formula, so we need to know T1 or A. And we also need to know how this is going to progress. From here, we know this is a multiplying progression since it's geometric. So we need to know this times r. I'll write this in a different color. We need to know some times r here, some times r here, some times r here. Well, to work out that times r, we really need to know how often we multiplied it. So really we had r times r times r. And I can write an equation to calculate 40 to negative 625 by rewriting it like this. 40 times r times r times r. Well, that's the same as r cubed. And if I do that, I end up at negative 625. And really, if I figure out times r, I can use that multiplier to work backwards to get to my t1. If I look at this equation, well, I have an equation that I can solve for r. And in solving for r, I'm going to divide these terms. 625 divided by 40. Okay, they share a common factor of 5, so this ends up being negative 125 over 8. To undo the cube, I'm going to cube root. So I end up with r is equal to the cube root of negative 125 over 8. Well, that's going to give me negative 5 over 2, or 2.5. And I can just check to see if that works. Times by 2.5 is going to give me 100. Sorry, negative 100. Times by 2.5 is going to give me positive 250. Times by 2.5 is going to give me negative 625. Yeah, I've got the right r. So to write the general formula, I have my r. I need to work out my t1, and I can just work backwards. Well, if I times going to the right, I'm going to divide going to the left. 40 divided by 2.5 works out, negative 2.5 works out to be 16. Dividing that by 2.5, I'm going to end up with 32 over 5. I think that's right. Let me just double check that. 16 divided by 2.5. Yeah, that's right. So the general formula, I can write Tn is equal to 32 over 5. My multiplier is negative 2.5. And then n minus 1, that counts the number of steps from 1 to wherever n is. So there it is. There's my general formula. Now, I could have also, instead of counting backwards, I could have just put it into the formula and solve for this a value, or the t1 value, algebraically using this formula, because I would have known the starting amount here. Actually, I would have known that one of the ending amounts. I could have used 40 or negative 625 in this spot. I know my ratio. Once I figured out my ratio, I would have known the n value that went with one of these two terms. In this case, this would have been T3 or T6. And so I could have used one of these pairs and plugged it in here, and that would have left me with only one variable to solve for in Tn.